So, dear students, good afternoon. Do you hear me?
Yes.
Yes.
Okay. So, I sent you an announcement that this lecture will be in English because after the last lecture, some students asked me to back to the format that lectures that I will teach you should be in English, and this lecture will be an experiment. But I ask you to fill the survey after this lecture and to get me some understanding what you want about the further lecture. So we're starting to deeply understand the ARMA and ARMA models. And the topic of today's lecture is a specification selection and parameter estimation for autoregressive moving average and ARMA models. Let's start by estimating the parameters of autoregressive model. It is simplest and clearly because the least square methods for estimating the parameters of this model works very well. We apply the least squares method, that is, we need to minimize the sum of the deviations of the actual values from the model. The cap here is a model estimate corresponding to some autoregressive process with given parameters. And this is the original empirical observable data. We apply the standard least square method. And here is the total number of available observations. P is the order of the autoregressive model. Here is the equation of autoregressive model itself. And minimizing this functional, we must take partial derivatives for each autoregressive coefficient and equate these partial derivatives to the zero. Further, solving this equation for each autoregression coefficient, we get the following system of the equations. It turns out that we have P equations corresponding to the order of the autoregressive model. And it is clear that this system of equation for finding the parameters of the autoregressive model through the least square determines the coefficients A1, A2, A3, and AP, depending on the autocorrelation coefficients, core 1, core 2, core P minus 1. That is, in fact, this system of equations shows that the coefficients of autoregressive model are completely depending on the autocorrelation coefficients. This is the main feature of the model. As a matter of fact, these autoregression coefficients pull over the main content of the autocorrelation coefficients of the analyzed time series, and therefore residuals of the autoregressive model are not autocorrelated. That is, if you build the model correctly, then its essence is that the residuals become independent random variables, pure white noise. The autoregressive model constant A0 is determined by the formula through the average value of the original series Y. We already went through this in the previous lecture when we considered how the mathematical expectation of the value Y is calculated. These are autoregression coefficients determined by this equation. This is the error variance it is considered as a sample variance due to model error. Model error is our original observed values minus the model itself. Epsilon t squared here is our squared model error. When we use the least square method to estimate autoregression model parameters, an important requirement is that we still have residuals of the epsilon t model that do not have autocorrelation. This is important theoretical requirement.
Excuse me, what is epsilon t again?
Sorry, please?
What is epsilon t?
Epsilon t is the residuals of the model. That is the difference between yt and yt with cap.
Thank you.
So, the important for forecasting is the properties that autocorrelation of residuals should be absent. To check this autocorrelation, the absence of autocorrelation, we should use the Ljung box test, while in the number of degrees of freedom, we must reduce the critical value of chi squared by the number of parameters of the autoregressive model. Theoretically, it is again recommended that if you nevertheless build an autoregressive model, found some autocorrelation in its residuals, then this order of P should be increased. But this rule can be avoided if you are interested in the simplest model and if you are interested in, by and large, tolerable forecasting, more or less correct forecasting. That is, in this case, for these purposes, sometimes you can leave the residuals of the model autocorrelated. Because once again, an increase in parameters autoregressive models do reduce autocorrelation. But in practice, as you will see from your experience, from your practice, it practically does not modify your final forecast in any way. The unbiasedness and consistency of our estimates is guaranteed by this lack of autocorrelation of residuals. But looking ahead, another effect is that the square of the residuals of the model, that is epsilon squared, has autocorrelation, while epsilon t itself should not have autocorrelation. This is the so-called arch effect, and this arch effect opens up prospects for constructing conditional heteroscedasticity models, the arch model and the Garch model. We will be aware of this a little further. So now the square of the residuals of the model, which has autocorrelation, should not confuse us.
Извините, можно вопрос?
Да-да-да.
Слайду. Не совсем все-таки понял, что вообще из себя представляет модель авторегрессии?
Модель авторегрессии — это вот эта правая часть уравнения. То есть вот смотрите, сам Y — это сами исходные данные, а Y с крышечкой — это модель авторегрессии. Модель авторегрессии — это вот такое уравнение.
Ну, я понял, что это уравнение, но что оно подразумевает? Для чего оно используется именно? Как пользуется авторегрессией?
Модель авторегрессии — это выражение текущего Y от своих предыдущих значений. То есть вот текущее значение Y модельное, есть некоторая функция от предыдущих значений этого Y. То есть регрессоры текущего Y являются предыдущие значения этого Y.
Хорошо, спасибо.
In addition to the least square method, the maximization of the likelihood function can also be used to estimate the parameters of the autoregressive model. The likelihood function for the autoregression model is the probability. This is the likelihood function, and this is the probability of simultaneously occurrence of observed events y1, y2, y3, and etc., provided that these events occurred as a result of the data generation process in accordance with the YT model with a cap. And this probability, by definition, we consider it as a probability of falling out the initial values of y1, y2, yp, the initial values for which we still cannot build an autoregressive model because we have no prehistory, and then multiply this probability by the probability of falling out yp plus 1 data, provided that the previous values are known and provided that they correspond to the capped Y model. So P here is the order of autoregression model. N is our final sample. And there the probability is already considered, provided that the previous values are known, provided that the model exists. This probability we need to maximize by sorting out the parameters of the autoregressive model. These conditional probabilities, the second part, is usually considered as a normal distribution with some mean and some variance. And then we have these conditional probabilities have a such distribution function, a distribution density function. So here YT is observed value. This is the average value. This is our variance. In the conditional likelihood function, these first initial probabilities are taken equal to 1. Because we cannot say anything about them. Because there is no prehistory and we cannot build a model. And in this case, the logarithm of the likelihood function is taken. The property of logarithm is very convenient to get rid of these products and turn them into sums. Therefore, the logarithm of the likelihood function is often used. This means that we have the logarithm of the likelihood function turns into such a value that here is n minus p divided 2 is the result of summation of the summation. N minus p here is the sum of all probabilities here. The first factor here, it turns into the first term. But the second factor of the exponent in power after taking logarithm, it turns into the second term. Now we maximize the function by iterating over the parameter estimate. In fact, here the estimation of the parameters is only in the numerator in the second term. Sigma, since it is supposed to be equal to constant, it also does not affect anything. And accordingly, with such a conclusion, the conditional likelihood estimates are identical here to least square estimates. The conditional likelihood function is needed for more advanced time series models, such as nonlinear models or conditional heteroscedasticity models. Therefore, we must introduce it so you really understand the general direction of constructing this function. And later, in more complex time series models, we will already say that the least square methods doesn't work. Only the conditional or exact likelihood function works there. The exact likelihood function imposes additional conditions on the distribution of initial probabilities, according to which we do not yet have a history and cannot estimate the model parameters. For example, they are assumed to be normally distributed with some standard error and some mean. And now, depending on these assumptions, the estimates may already differ from the methods of least squares. It follows from this first equation that as the number of observations tends to infinity, the exact and conditional likelihood estimates converge. This is the so-called asymptotic equivalence. Therefore, this terminology must be understood: how the likelihood function is constructed, how the conditional likelihood is estimated, how the exact likelihood is estimated. For the autoregression model, we don't really need these functions because they give us the same result as the least square method. But in the future, they will be very useful to us. After we talked about estimating the parameters of the autoregressive model, the question of choosing the order P of the autoregressive model remains unanswered. That is, which autoregressive model should we train on the existing data? Autoregressive model 1, IR2, or IR7? This remains unclear. What are the approaches here? The first option is when we iterate through the specification of the model one by one, each time increasing the order of P, and as a result choose the specification in which there is no autocorrelation in the residuals at a given significance level. Autocorrelation in the residuals is checked using the Leung box test. That is, we sort through the model one by one. First, IR1, we check the autocorrelation of its residuals. If there is no autocorrelation in the residuals, then we take IR1. By the way, I missed it, but in fact the simplest model is IR0. So generally speaking, pure formally, we should start with IR0. Firstly IR0, then IR1, IR2, and so on. But this way is a bit long and routine, so options 2 also exists. It consists in the fact that to select the order of the autoregression model, you can use the partial autocorrelation function, PACF. This function is built as follows. The autoregression models are sorted one by one, the first, the second, the third. Here it is not necessary to sort out the 0, 1. And these coefficients are estimated at corresponding yt minus 1. That is, if the first model is the coefficient at yt minus 1. If the second model is the coefficient at yt minus 2, that is AY1, A22, and A33 for the third equation, and so on. These coefficients, these diagonal coefficients, make up the PAC function. Or it is possible to say in other way, the significance of these coefficients is the PAC function. Next, this PAC function consisting of these coefficients, the diagonal coefficients of the autoregressive models, is already being checked for the significance. It is known that where our coefficients become insignificant, that is, it is already greater than the optimal autoregression parameter. Then the distribution of the roots of n multiply on these autoregression coefficients has a normal distribution with parameters 0 and 1. That is, using this property, in fact, a partial correlation function allows us to test that the null hypothesis H0 is that the optimal order P of the IRP process corresponds to a certain order K. K we sort through 1, 2, 3, 4, 5, and etc. And we test this hypothesis against the H1 that the optimal parameter is larger, that is P equals to K plus 1. Not current K, but the next. And if this statistics is the root of n multiplied by the coefficient AKK is greater than 1, then H0 is rejected. If it turns out to be less than 1, the normal distribution 0, 1, then H0 is accepted. That is, in other words, we simply build this PAC function in the application package and determine the parameter P based on the significance on the PAC coefficient. That is, as soon as the PAC parameter becomes insignificant, we immediately cut off the following autoregression legs, not using them and not including them in the model. Also, since our IRP is quite normally estimated by least square method, we can use R squared or R squared adjusted to assess the descriptive ability of the model. But choosing the order of the model based on this criteria is not recommended. Just as it is not recommended to choose the order of the model based on the t-statistic. That is, if you immediately included the IR3 model and just looked at the significance of the coefficient of the t-statistics, then you may experience overfitting. All these coefficients can be significant, but in fact, PAC is a more accurate measure for choosing the order of a model. It often points you to IR2 or IR1. That is the main summary. The order of autoregressive model is recommended to be estimated based on the PAC function.
Можно задать вопрос?
Да.
Насколько я поняла, сейчас мы обсуждали оптимальное количество лагов в модели авторегрессии.
Да.
Насколько я поняла, вы проговорили, первый подход — это на основе F-статистики.
Не F-статистики, на основе автокорреляции остатков.
Автокорреляция остатков. И это был первый вариант. Второй вариант — это PAC функция.
Да.
Не могли бы вы еще раз проговорить на русском, чем она отличается от первого варианта?
У нас сейчас будут примеры, и я думаю, что там будет полегче. То есть, если по-русски, вкратце, пак-функция — это вот эти коэффициенты диагональные в моделях авторегрессии. То есть коэффициент А1,1, коэффициент А2,2, коэффициент А3,3, коэффициент А4,4. Вот пак-функция — это вектор из вот этих коэффициентов. И дальше эти коэффициенты проверяются на значимость. И вот дальше у нас будет пример, и в принципе вам будет понятнее.
Это что-то типа big. То есть есть такой
Нет,
боец?
это не бик, это совсем другая вещь. Бик — это просто коэффициент 1, а здесь будет целый вектор.
Поняла вас. Спасибо.
So let's consider the first example. We have a DGR file in our handouts. There is a price level in the United States. Based on this price level, we can calculate the first differences. This will be monthly inflation. The file represents the logarithm of the price level, so the first differences are monthly inflation in terms of log returns. Here it is necessary to predict this monthly inflation. For this, it is necessary to build an IRP model. In the first step, we calculate the PAC function. That is, we run the function. It is in the handouts. There is the file IR model example. This file contains all the syntax of used function. So let's calculate this partial autocorrelation function. Here is, you can see the result. This is the value of the partial autocorrelation function at the level of 5% significance. These dotted blue lines means the significant lines. All values inside of these lines means insignificant PAC coefficients. So, and based on this data, we are accordingly cut off those k that are significant. So the k is the x-axis. That means lags. So here we can see that exactly first 4 parameters are significant, respectively, which means that IR4 is definitely needed in this case. That is, at least IR4 we should build. IR5 or IR6 is already in question. The insignificance is visible here. IR8, IR9 are slightly significant. Maybe IR11. That is, here on the verge of this significance, we have some alternatives. This is a very important choice of the researcher, that what he needs. IR4 for sure. IR6 questionable. IR9, IR11 also questionable. So here we have 4 alternatives. Well, you can also include IR20 in the model if for some reason it is necessary. But this inclusion of additional legs of the model is necessary for theoretical purity of the model in order to completely eliminate autocorrelation in residuals. But these distant legs will give practically nothing as an increase in accuracy of forecasting. That is, there will be such a microscopic improvements in the accuracy of the forecast that it is quite possible to ignore these distant lags and not include them in the model. That is, I would say, that from the standpoint of forecasting accuracy, the first four legs will be influenced on forecast, and everything else will be such a small influence that it can be neglected in practice. Although theoretically, of course, all of this should be included in the model. Вот эта пак-функция, про которую вы меня спрашивали, и здесь 4 первых лага четко значимы, а вот остальные под вопросом. Вот эти вот лаги под вопросом, это как раз дискуссия, надо ли это включать в модель или нет. Эта дискуссия, она нигде однозначно не определена, ее выбирает исследователь, выбирая между точностью прогнозирования, которую он хочет, и теоретической частотой модели.
Извините, можно вопрос?
Да.
А вот мы видим на графике, что после там есть незначимые лаги, а после, например, 20-й лаг, который удаляется от первого, он значим. Но не будет ли у нас переобучения, если мы, например, возьмем 20-й,
Будет.
а не 10-й? А как тогда определить оптимальную? Может быть, есть какие-то другие критерии?
Ну, послушайте немножко, да, вот что мы дальше будем делать. То есть пример-то продолжится. То есть я понимаю все ваши вопросы, они все очень хорошие, но чуть-чуть выдержите паузу, ладно? So the next step is to estimate the parameters of the AR4 model. This is our base model, which we defined on the previous slide using PACF. Here we call the linear model function, LM. And here we have a formula to the first CPI difference, that is our inflation is the function of four regressors. Inflation with first lag, inflation with second lag, and that's all. Here I'm using LM function for now, while on the next slide we'll look at the ARMA function, because both can be used for estimating IR parameters. But you should understand both of these alternatives. Of course, the ARMA function is more widely used for further testing when you are more experienced with predictive models. In future, you will, of course, not use a LM function, but use the ARMA function. Here, there is given distribution of residuals of this model, and here they are coefficients. Intercept is our parameter A0, estimates, standard errors, t-statistics, p-value significance. Regression coefficients at first lag, regression coefficients at second lag, and that's all. Here you can see the R-squared adjusted. This is what we see in IR4 model. Accordingly, here you can see the IR6 model, which is an alternative. And we must also understand it, compare it with IR4 model. Here, two legs are added to this LM formula, leg 5 and leg 6. Leg 5 are not significant at 10% level. L6 is significant at 5% level. That is, you can add regressors and observe the improvement of R-squared adjusted. But still in autoregressive models, this is not the main criterion for making decision. That is based on R-squared adjusted. One cannot say that IR6 model is better than IR4 model. So we can see the improvements of R-squared adjusted from 1062 to 1096, and but this is not improvement of the time series model. The main criteria for finally choosing the model is the autocorrelation of residuals. That is, once again, the meaning of using autoregressive moving average and ARMA models is not only forecasting. It is, first of all, the correct inclusion of time series autocorrelation in the model. And if we include this autocorrelation correctly, then the residuals should not have autocorrelation. Therefore, we must check the residuals of our model for autocorrelation in conclusion. To do this, we build an autocorrelation function ACF, not PAC, but ACF. It's just a regular legged autocorrelation coefficient. And we see the autocorrelation coefficients as significant. It is clear that there are some outliers, especially on 20 legs, which we have shown on the previous PAC slide that it is significant, and we did not include it into the model. Therefore, it is natural that we did not include it in the model, and here in the residuals it was translated. This autocorrelation is on the 20th leg. But more preciously, we run the Ljung box test. In the handouts, there is a command to call this test. So I translate here to the comment. And we see the degrees of freedom. Degrees of freedom equals to m in our standard formula of Ljung box test. So this number of degrees of freedom for residuals of the model is determined as the difference between leg 7 in the comment. This leg 7 determines as a natural logarithm of n of the available data for analysis minus degrees of freedom, and degrees of freedom PDF. Degrees of freedom means the number of the order of IR model. Therefore, for testing the IR4 model, we type here leg equals to 7 and fit the F equals to 4. And therefore, in the output on Ljung box test, we see the degrees of freedom equals 3, and this 3 calculates as 7 minus 4 for our IR4 model. But for the IR6 model, Ljung box test run with fit df6. This 6 is equivalent to the order of the model. And in the output of the IR6 model, we see the degrees of freedom equal to 1. This 1 is calculated as 7 minus 6. And for both tests for both model, we can see the same p-value of autocorrelation of residuals, 0.2. And this means that the probabilities of error, if we reject the null hypothesis, is higher than 10% significance. So therefore, our conclusions should be that we cannot reject the null hypothesis of absence of autocorrelation in both models. Therefore, both model is suitable on this data. And manage on this conclusion, we check that IR4 model is better than IR6 due to the savings of the parameters. So here the conclusion of our example. The final specification of IRP model for monthly inflation is IR4 model. Here the final coefficients of the model, and this is the coefficients of A0, and this is a standard deviation of the residuals. What else important? If you use the ARMA function to evaluate the autoregression parameters, so I used the LM function in the previous slide, and if you use the ARMA function, you will have its syntax in the IR example file in your handouts, and take the syntax from there and repeat the calculation. And that application of this ARMA function will give you the same autoregression coefficient. Well, in the fourth sign, it is slightly different. So, for example, ARMA gives you 1966 and LM function gives you 1961. This is because there is a already difference between the exact likelihood function and the least square method. But the drift coefficient, it is very different. It is 2 times different from the ARMA function 0024 and from the LM function 0012. That means that the previous coefficients 012 are correct, but this drift from ARMA function is something else, but not a zero coefficient. You need to carefully read the help for the ARMA function in R, and then you will see that in the ARMA function under the drift coefficient or intercept, depending on which query you enter, a selective math expectation for the analyzed series is presented. And when you have a sample expectation for the analyzed series, you can calculate the coefficient A0 from the formula for the average for the IRP process. We recall the previous lecture, or recall what was written on the first slide today, and the coefficient A0 is calculated from this equation. That is, in order to turn this 0.24 coefficient into something like 0.12, you must calculate A0 using this formula. Then A0 will turn out to be close to this value. This is the small important feature of this function, so please pay attention to it. That is, the drift parameter in the ARMA function is not a zero from the autoregressive process. We are starting to study these models deeper and deeper, and now consider the following example. We have data on the logarithm of annual GDP per capita for the United States at constant prices. This is data from earlier of 19th century. This is a Great Depression of 29th, 34 years, the decline in GDP. Then Roosevelt's economic policy. These are the post-war years. And then the history after the Second World War. This is a small crisis of 2008. We need to predict this logarithm of annual GDP per capita in the United States at constant prices. That is, we run PAC function and see the following feature. PAC with order 1 is close to unity. That is, it is clear that only the first leg is significant and there are no other alternatives. Here is what we conclude based on PAC. We need to construct an autoregressive model with order 1. We estimate the parameters of IR1 model. It turns out that the coefficient at the first leg is 1, 0, 0, 2. The intercept, that is A0, using LM function is minus 0.005. Now we check the autocorrelation of the residuals and see a significant first leg autocorrelation, a significant fifth leg autocorrelation, fourth leg, and the launch of Lewing box test indicates that the residuals are strongly autocorrelated. That is, the probability of making a mistake by rejecting the hypothesis of absence of autocorrelation is 0. Through the PAC, we see that we have no alternative. But here it is obvious that if we increase the order of the model, then somehow it is not clear. PAC probably doesn't work. But there is a small subtlety here, which is connected with this unit. In fact, the autoregressive model has one particular feature that must be theoretically considered. It is called a unit root in an autoregressive model. And the fact that a unit root has turned out here is evidenced by this coefficient close to 1. It can be 0.999, maybe a little higher than 1. That is coefficient close to 1 in the regressors with a lag of 1. Let's look at this unit root problem theoretically. Let we have some process IRP. We represent it as a polynomial of a shift operator. Transfer all these coefficients to the left side, take it out of brackets, and use the shift operator. Having solved the resulting characteristic equation, we expand this polynomial into factors. And let one of the roots, Z1, Z2, Zp, of the characteristic equation be equal to 1. Equation. What will happen then? Then we have that some one of the factor turns into y1 minus L. The remaining factors form a polynomial with p minus 1 order, denoted as A asterisk L. So A asterisk L is the polynomial of p minus order, because one order polynomial goes to 1 minus L due to unit root here, because one of this z are equals to 1. Here is what we got. If we multiply 1 minus L by yt, then we get a polynomial degree p minus 1, multiply on yt minus 1, yt minus 1, yt minus 1 equals to epsilon. And here we have delta y. or the first difference, yt minus 1 is delta y or the first difference. And now, if we apply this difference, multiply it by this polynomial, transfer the results of the polynomial to the right side, then we get that our process IRP having a unit root where one of the roots of the characteristic equation is equal to 1. That is in fact the same as the process of autoregression on order p minus 1, on the first differences delta y. That is, delta y is the sum from 1 to p minus 1, multiply the new coefficients a asterisk, multiply by delta y with a lag plus epsilon. That is, this is the result. If IRP process for yt has a unit root, then it turns out that the process itself is formed as yt is equal to yt minus 1 plus delta y. Is the autoregressive process with p minus 1 order. Similar theoretical conclusion is valid for ARMA PQ process. We have ARMA PQ process. These are autoregression coefficients. These are moving average coefficients. And if we represent the left and the right parts as a polynomial from the shift operator, and at the same time on the left side where we have an autoregression polynomial, we get a unit root there, at least one unit root, then we transform these into what the process ARMA PQ correspond to the process ARMA P minus 1Q, but on the first difference delta y. Here too, autoregression from first differences. That is, this decrease in the order of the process is empirically very important. Here we theoretically showed that this is a decrease in the order of the process. That is, if there is a unit root. This process turns into a process of order p minus 1, but on the first differences. Здесь мы рассмотрели теоретический пример, как с единичным корнем процесс ARP на показателе превращается в процесс ARP минус 1 на первой разнице. Этот единичный корень он означает, что процесс запущен с меньшим порядком, но на первой разнице. И это очень важное эмпирическое свойство, которое вот не позволило нам решить эту проблему с американским ВВП. Let's look here at example to understand these theoretical properties clearer. Here we have some ARMA 2-1 process, which is described with this equation. Consider whether there is a unit root in this process or not. We will transfer the autoregression parameters to the left side and represent this record as a polynomial of a shift operator. Here we have it converted. Yt is rendered here. It will be 1 minus 1.2 plus 0.2 multiply L, like operator, like squared. and the roots, it turns out to y1 minus 0.2 multiply L times 1 minus L multiplied by yt. On the right side, y1 minus 0.5 L remains, multiply on epsilon t. And now we see that the characteristic equation for autoregression has a unit root. It is shown here because here we will have a unit. And accordingly, this unit root allows us to move on to the first differences. That is, this is the product of the second factor by yt. We open it as yt minus 1. That is lyt, it will be yt minus 1. lyt will be yt minus 1. And here we have the first difference. This is the first difference. And now when we already reveal the first difference and leave delta yt itself on the left side and transfer delta yt minus 1 to the right side, it is respectively multiplied by 0.2. And the sign then changes on the right side during the transfer. Then we get the process ARMA 1,1, but on the first differences. That is, this means that this is initial equation of the ARMA 2,1 processes. It exactly corresponds to this equation, but on the first differences. Theoretically, this is the same ARMA 2,1 on yt and ARMA 1,1 on the first differences. But empirically, the question is how do you estimate the parameters from real data on the original series or on the first differences? The empirical error due to the estimation of parameters on an indicator with a unit root becomes very large. Therefore, it is very important to test this unit root and the discussion and the equation of our ARMA parameters. Estimations taking into account the unit roots should already occur either on the initial series or on the first differences, if the unit root is present. After this theory and understanding, the question arises of how to test this unit root on empirical data. And in this case, when testing this unit root, one speaks of the hypothesis that the exponent of yt is non-stationary. These two concepts are now closely related with the unit root of our model, and yt is non-stationary indicator. For testing non-stationary, the most well-known test is the Dickey-Fuller test, DF test. How is it built? We have a first-order autoregressive model. Yt is A1 multiply yt minus 1 plus A0 plus error. Parameters A1 and A0 are estimated using the least square method. Testing unit root means testing the hypothesis that this coefficient A1 is equal to 1. And this can be verified using standard test statistic. Dickey-Fuller showed that under the null hypothesis, A1 equals to 1, these t-statistics does not have a t-distribution, even asymptotically. The correct and critical values for these statistics are completely different. They are presented in our table below. T is our sample size. These are critical values of 1 and 5% levels. And there are 3 versions of this test. But I will say this a little later. Now, using our theoretical knowledge with a unit root, we will rewrite this autoregressive model in a slightly different form. That is, we will replace yt with yt minus 1 plus dt, delta t. And we get the usual type of the model used in this test, that the first difference is a1 minus 1 multiply yt minus 1 plus a0 plus epsilon t. Here we have some coefficient. Let's denote it as a1 asterisk. If a1 equal to 1, then a1 asterisk is equal to 0. In fact, the regression is tested for the significance of the difference of this coefficient a1 asterisk from 0. Its difference from 0 is equivalent to the fact that a1 is equal to 1. The hypothesis that is being tested is that this a1 is equal to 1. This means non-stationary, and the correctness of the model on the first differences. In this case, we only get a0 on the first differences. That is, the IR0 model arises on the first differences. The test is carried out against the alternative that a1 is not equal to 1, which means that the yt is stationary. This means that the original IR1 model is correct. When is a specification without a trend, without a constant used, and when a specification with a trend used? If considering H0 for some reason, we have motives to believe that the original tested model should have a theoretical constraint A0 equals to 0. Then we use the version without a constant, without a trend. In practice, I have never seen or met such justification anywhere. In some cases, a situation really arises when we have theoretical assumptions about the absence of a constant. But these are such rare situations which are aware of such things will not rise. A version with a constant and trend, it includes model specifications with AT multiply T added. AT is a sum trend factor and T is a linear time. Constant and trend testing is widely used to test so-called trend-stationary models as an alternative. The fact is that before the advent of these autoregressive models, trend-stationary models were widely used in econometrics, and at that moment, in order to compare these specifications, i.e. the presence of a unit root versus the trend-stationary hypothesis, this version of Dickey-Fuller test with a constant and with a trend was developed. To summarize, when you just see a series without any additional features, you are using a version of the test with a constant and without trend. An extension of the Dickey-Fuller test is the ADF test, augmented Dickey-Fuller test. It considers as a null hypothesis not only the IR1 process, but also the IR2 process, IR3 process, and in general IRP process. That is, we have a null hypothesis that process Y has a distribution or a pattern according to a second order autoregressive model. We represent yt through yt minus 1 and delta y. We do the same for yt minus 2. This is yt minus 1 minus delta yt. And accordingly, these coefficients go here, and here we have such a specification for testing that the first difference is the lag value of the initial series with such coefficients minus a2 multiply dy delta y t minus 1 plus a0 plus epsilon. The equality of the coefficients a1 plus a2 to 1 is tested, not a1 equals to 1 anymore. And the sum of the autoregression coefficients must be equal to 1, so that these brackets in fact is equals to 0. And here is the same for the IR3 model. The same transformation is done, and it turns out that we are testing the equation on the first difference, that is the sum of the coefficients a1, a2, a3 minus 1 multiplied by the original series with a lag and by regression with the first difference with a lag. The first difference with 2 lags. And the same can be obtained by analogy with these coefficients when testing the IRP process in general case, tested using standard statistics. The null hypothesis is tested, the sum of the autoregression coefficients is equal to 1, that is not stationarity or presence of a unit root. Against the alternative hypothesis, the coefficient is not equal to 1, that is stationarity. The critical values are same as those of the Dickey-Fuller tests, and there are also 3 versions. The main one with a constant and without trend. This order of the autoregressive model is important characteristic of Dickey-Fuller test. When you run this Dickey-Fuller test in R, you will need to specify the number of legs for your autoregressive model there. This is the number of legs for your autoregressive model that you fit according to the path of your delta y, i.e. the first difference of the indicator analyzed for stationarity. Accordingly, by setting this number of legs that are tested in the extended Dickey-Fuller test, you already get one or another specification, but which affects the p-value of your hypothesis about the non-stationarity of the time series against the hypothesis of its stationarity. Except the Dickey-Fuller test, there are 2 other econometric tests for stationarity. The first test is called the KPSS test. The second test is the Phillips-Perron test. PP test repeats the ADF test very much. Test statistics are set a little differently there, but there are studies that show that the Phillips-Perron test gives a higher probability of error. That is, in practice, I see no reason to use this test in addition to the Dickey-Fuller test. But the KPSS test has some features. And the fact is that the KPSS test is designed in the opposite direction. That is, if our Dickey-Fuller test considers the null hypothesis, the series is not stationary. There is a unit root, then it controls the probability of the first type error, that H0 is incorrectly rejected. But the KPSS test was developed in opposite direction. It was developed on the basis of the theoretical hypothesis that the series is stationary. That is, when we have theoretical grounds to believe that the series is stationary, then applying the KPSS test. And it accordingly controls the probability of a type 1 error. That is the probability that we incorrectly reject. We incorrectly reject H0. The simultaneous application of these two tests gives rise to uncertainty and discussion, which are often sometimes understood that this uncertainty cannot be revealed in any way. Here the logic is such that if, according to some theoretical assumptions, you have reasons to believe that these indicators should be stationary, then you apply the KPSS test. If you do not have such theoretical grounds, and you apply the null hypothesis that the series is non-stationary, then you use the ADF test. Everything else is this synthesis, where one method say one thing, another method say another. This is already a matter of some theoretical discussion, scientific discussion, but it should not much concern students. In addition, the students must also remember that any series, such as GDP or company's revenue or profit, it exists not only for one company or country. It exists for the similar companies or similar countries. That is, in other words, these indicators are members of a certain family, and these tests for stationarity should be applied more accurately, not to one member of the family, but to the whole family. And here already there are grounds for justifying stationarity based not on a single series, but on the basis of a theoretical assumption under test results for the entire family. For example, testing with the Dickey-Fuller test of GDP per capita is widespread. For most countries, GDP per capita is a non-stationary process, but for some countries, at a 5 or 1% significance level, GDP per capita is a stationary indicator. How to be here? Could it be that the GDP of France is a stationary process, while the GDP of, say, the United States is a non-stationary process? That is, if you are faced with such uncertainty, theory or econometrics tells you that you need to accept the hypothesis of stationarity for the whole family. That is, if for most countries GDP per capita is non-stationary, then it is also non-stationary for France, even though the DF test shows its stationarity. That is, here, when applying the stationarity test, you need to take into account such nuances. In econometrics, not everything follows a standard template. That is, econometrics itself and these tests themselves, when you use them for justification, they do not come down to just blindly following the rules. You must understand the alternatives, you must understand the subtleties that are discussed here in the course of the lecture, and in the course of your practical works, you will also come across it. And accordingly, taking into account these subtleties on the basis of component reasoning, you should already be making informed decisions for which you personally, as a researcher, take responsibility. So we have a lack of time, and for this lecture, I must explain you only last slide, I believe, and other slides I think we will discuss in the next lecture. Maybe it is possible for you to see the Russian language lectures and to be prepared to the seminars at Saturday. So far we have tested the original series for stationarity, and in case of its non-stationarity, we have received the basis for the constructing an autoregressive model on the first differences. However, it may turn out that the first difference will also have a unit root. That is, the first difference in economic indicator also need to be tested for stationarity. In this case, the regression that is being tested looks like there is a second difference of the initial series, delta 2yt. This is a regression from the first difference with a lag of 1, and the regression from the second difference with a lag of 2, 3, and so on. This is multiplier is being tested. This multiplier is being tested. The sum of the autoregression coefficients minus 1 is equal to 1 or not. If the first difference turns out to be non-stationary, then accordingly we similarly pass to the second differences, and so on. For economic data, one doesn't have to go farther than the second differences. That is, again, according to the totality of applying tests to the members of the entire family, most economic indicators are either stationarity in themselves or stationary in the first difference. It is very rare when an economic indicator is stationary in the second difference. Never when economic indicators are no longer stationary in the third difference, and so on. This necessity of testing the unit root hypothesis on the variance differences generates the ARMA PQK model. ARMA means autoregressive integrated moving average model. Integrated is our period, the order of taking the differences, which is denoted by the letter Q. P is the number of parameters of the autoregressive process. K is the pure parameter of the moving average process. And Q is the order in which the difference is taken. Well, as a matter of fact, this ARMA model is writing in this way. If Q equals 0, then it is on the initial y that the moving average autoregressive model is built. If Q equals to 1, then the ARMA model is based on first differences. If Q equals 2, then the ARMA model is built on the second differences. But these are in fact some generalizations. So the R function that allows us to build an ARMA model is actually not called an ARMA function, but an ARMA function. And there we mean that you can specify this order of taking the difference to build a model. So we run out of time.
May I ask a small question, please?
Yeah, of course.
Can we somehow distinguish stationary series and non-stationary series on the graph, or it's impossible?
Yes, of course, but this is some simplification. For exact distinguishing, you need to run the Dickey-Fuller test. But for simplification, you can show, you can see the graph, and if you see the trend of the data, for example, the increasing of the data or falling the data, then you with high probability can conclude that this data is not stationary. But in other case, if you don't see the time trend in the data, this data is horizontal. It varied within some range. Then with high probability, you can conclude that this data is stationary.
Okay, thank you.
Okay.
Можно еще такой вопрос? В чем лучше делать домашнее задание, в ARMA или в Excel? Что поможет нам на семинаре?
Ну вот то домашнее задание, которое было, не семинарское задание, а домашнее, его в принципе можно сделать в Excel, потому что в R его будет сложнее сделать. Поэтому тут вы выбираете сами где. А само семинарское задание, где вам надо будет строить тесты Диckey-Фуллера, строить модели ARMA, регрессии, его в Excel уже выполнить тяжелее, поэтому, наверное, его все-таки придется выполнять в R. То есть наши семинары, в принципе, основаны на использовании R, так что вот завтра уже будут семинары с R.
А еще скажите, пожалуйста, я правильно понимаю, что завтра на семинаре будет материал 2 лекций, предыдущей и сегодняшней?
Да, совершенно верно. Поскольку мы не успели большую часть сегодня пройти, я вас прошу просто хотя бы посмотреть эти лекции, если будет возможность послушать варианты на русском, потому что вот тот материал, который мы сейчас не успели пройти, он, в общем-то, уже к семинару завтрашнему понадобится.
А еще вопрос по оцениванию домашних заданий. Они же не оцениваются или все-таки оцениваются?
Оценивается работа на семинаре, включая само домашнее задание. То есть лектор может, преподаватель на семинаре, он вас может спросить о выполнении домашнего задания, и это будет часть вашей оценки за семинарскую работу.
Угу. Но прикреплять в ЛМС его не обязательно?
Его не надо никуда прикреплять, то есть мы сделали так, что официально сдавать это все не надо, вам официально надо будет сдать только отчет по семинару, если вы на нем не присутствовали, по какой-то причине пропустили, а если вы пришли на семинар, то вам оценка за семинар будет объявлена преподавателем на самом семинаре, и этого будет достаточно.
Хорошо, спасибо большое.
Угу. Хорошо. Okay, thank you very much. Good luck. See you next week.
Thank you. Goodbye.
Thank you.